test, testing joint hypothesis. So now we have learned to test a single conjecture about one or more parameters using t-test. Our null hypothesis is something like this. Say beta 2, we're going to test beta 2 equal to 0 or not. We can have two types of alternative. One is two tail, which beta 2 is not equal to 0. The other is one tail. Say beta 2 is less than 0 or bigger than 0, depending on our theoretical expectation on the signs of beta 2. In this week, we will study how to test hypothesis that involves more than just one conjecture. So more than one, here we have one equal signs. Now, our null hypothesis will consist of more than one equal signs. We call this joint hypothesis. It's a null hypothesis with multiple conjecture with more than one equal signs. So for example, our null could be beta 2 is equal to 0 and beta 3 is equal to 0. So we have two equal sign here against the alternative, which is beta 2 is not equal to 0 or beta 3 is not equal to 0 or both. Let's pause for a moment. Think, how can we test for such kind of joint hypothesis? So look at the null. Now, under the null, we are actually imposing a restrictions on the models. We are saying that beta 2, so our model is y is equal to beta 1 plus beta 2 x plus beta 3 z plus L temp, suppose. And if under the null, if our null is true, then we are saying that beta 2 and beta 3 should be equal to 0. So under the null, our model will be look like this. Y is equal to beta 1 plus e. There's only one constant terms here. So we can think this is our restricted models, and this is our unrestricted models. And if our null hypothesis is true, then these two models, estimation, the gradient of these two models should be similar to each other, right? There shouldn't be any significant difference. If we observe significant difference, then we have evidence to reject the null. That's the basic idea of this joint hypothesis testings. But we need to be more precise about what does it mean by significant difference. Okay. So let's be more precise here. It's best to look at an examples. Continue with our example of Big Andy's burger bun. We have estimate of the model previously. So let's continue with this. Suppose our model is this. Sales is equal to beta 1 plus beta 2 times price of the burger plus beta 3 times advertising expenditure. We also include the square terms of advertising expenditure. So now we allow for this advertising to affect the sales revenue non-linearly. So if beta 4 is positive, then we holding price constants. Then we can draw the graph of sales against advertising expenditure, something like this. If positive, then we have parabolic shape of the curve, the graph. So in these cases, if beta 4 is positive, the implication is that we should advertise as much as possible up to go to infinity. And we can actually see this is sales revenue, and let's draw the 45-degree line. Remember, when we advertise, there's a cost associated with advertising, right? So which is the money you spend on advertising. So the difference between this red curve and the blue line is actually profit from advertising. And we can see that, well, when the 45-degree line is above the curve, then the firm is making a loss. Say, for example, say firms and this Burger Bond spend this many dollars on advertising. Sales revenue at this level, cost at this revenue at this level, there's this many loss. And if it's at this level, then we see there's a profit, and profit is going up. Okay, so the implication is that Andy's Burger Bond should advertise as much as possible if beta 4 is positive. If beta 4 is negative, we have a different situation. Again, vertical axis is sales revenue, horizontal is advertising expenditure. So something like we have this this inverse U shape of this curve. And let's draw the 45-degree line. We can see that, okay, they exist a level, say, probably on top of this, where the slope is 0. This level of advertising expenditure is optimal. It's best, maximize the profit that Andy's Burger Bond will receive. So now our model allows for the marginal impact of advertising on sales revenue to be nonlinear, okay? And we want to test whether beta 3, beta 4 is equal to 0 jointly or not. So now hypothesis is this. Ultimately, hypothesis is at least one of them is not equal to 0. So under the law, we have so our unrestricted model is this. Okay, that's our unrestricted model. We impose the restrictions, we get these restricted models, and we can also think in I'm writing the error term as E2 now. So we can also think that E2 is equal to beta 3 times advertising plus beta 4 times squared advertising plus original E. Okay, we can think this. So assuming normality distributions, okay, then under the law, E2 and E should be similar. They should resemble each other. So what do we mean by similar? Okay, to see this, let's first standardize the error terms. Okay, let me have a side note here. Suppose we have a random value of x, which is normally distributed with mean mu, variance sigma square. Then we can standardize this x. Say let's call it z. Will be by doing this transformation. X take away the mean divided by the standard deviation, and we can show that this is now standard normally distributed with mean 0, variance 1. Okay, so let's first. Okay, that's a side note. Remember our E we assume that it's normally distributed with mean 0 and the variance sigma squared, right? So we want to divide E by sigma. So E by sigma, divided E by sigma. Now it will be standard normally distributed. And divided E2 by sigma. So under the null, our null hypothesis, bear in mind that is beta 3 and beta 4 are equal to 0. Under the null, it is also standard normally distributed. So the variance should be the same. The variance of E2 is the same as variance of E, which is sigma. In contrast, if the alternative is true, so now our beta 3 is not equal to 0, beta 4 is not equal to 0 anymore. At least one of them is not 0. And our E2 will contain random variable advertising expenditure. So intuitively, you think that it should have more variation, more variance in it. And this is indeed the case. So here sigma 2 square is the variance of E2. So now we divided E2 by sigma. So the variance is still a normal distribution, but the variance now is sigma 2 square divided by sigma square. And we should know that sigma 2 square will be bigger than, at least as large as sigma square, because E2 contains advertising, these additional random variables. Okay, so now under the alternative E2 divided by sigma, the variance is this many. In contrast, the variance of E divided by sigma is 1. Okay, so for either case, either null or alternative, we see that the variance of E2 must be bigger than variance of E. Okay, must be bigger than or equal to variance of E. And this observation is important for our test HD. And bear in mind the variance here is constant value. It's not random variable. Okay. So now E2 divided by sigma, E divided by sigma is normally distributed. Let's square them to get rid of the negative signs. And if a variable x, let's call x1, is standard normally distributed, so then its square term is chi-squared distributed with degree of freedom 1. If I have many chi-square distributions, say with some 2, suppose, then this is chi-square distributed with degree of freedom 2, so on and so forth. Okay, these are probability knowledge. Okay. So we square them, square one of the error terms, standardize them, square them, so we get chi-square distribution with degree of freedom 1 under the null. Okay, bear in mind this is under the null. We can sum them up, add them up from observation 1 to observation n, so we get square. Under the null is chi-square distribution with degree of freedom n. Similarly, this is restricted, this is unrestricted model. Then we can divide it by n. Okay, this quantity divided by n, and doing so we want to apply this weak low or large number. So we want to let n goes to infinity, and under the nulls, then we can show that this quantity eventually goes to 1, converges to 1 in probability. Similarly, for this converges to 1. So under the null, they should be exactly the same. The difference is 0. Under the alternative, this probability limit of these terms, it goes to these terms, sigma square divided by sigma 2 square divided by sigma square, and this is bigger than 1. Okay, and for the unrestricted model, it still converts to 1. So observe that these two terms, we can check the variance, the ratio of these two variance, or percentage difference of these two variance, to find evidence of whether our null is true or whether we can reject or cannot reject the null. Okay, that's all this manipulation is doing. Okay, so let's look at the quantities, these quantities. Okay, so this is the quantity that in our previous slides for the restricted model, and this is the quantity for the unrestricted model. So we take the difference of them, then divided by the quantity of unrestricted model. So we are kind of scaling, looking at percentage difference in a sense. Okay, so we can multiply both top and bottom by n, so we can cancel out the n. We can also cancel out the sigma square, and bear in mind we don't know sigma square, so it's good to cancel it out. Okay, sigma square, multiply both top and down by sigma square, so we get this quantity. However, okay, suppose we have this quantity. Okay, then this quantity should be close to 0 under null and bigger than 0 if the alternative is true. So if we get the value of this quantity is far away from 0, then we find the evidence to reject the nulls. Unfortunately, we do not observe the error terms, okay, directly. But on the one hand, unfortunately, we do not observe the error terms directly. On the other hand, fortunately, we can estimate them. So we have the estimated version. How do we estimate this? So we for the restricted models, so we regress y against sales against the price and predict the residuals. So this is the residuals of the restricted models, and this is the residual estimated by the residual of the unrestricted models. So given previous quantity, which is unobserved to us, but we can find an observed version of that. Okay, so this line of reasoning gives us a statistics, which is F statistics, which is sum of E hat 2 squares. So sum over all observations minus the sum of E hat 2, which is unrestricted models. So look at the difference of them. So these terms now is actually sum of square errors for the restricted models, and this is sum of square errors for the unrestricted models. Observe that this SSER should be at least as big as SSE unrestricted models. Okay. Then divided by J, we divided it by J to correct for degree of freedom. That's the numerator. For the denominators, we sum the squared errors for the unrestricted model divided by n minus k to correct for the degree of freedoms. We can show that this test statistics is F distributed with numerator degree of freedom J, denominator degree of freedom n minus k. And we can use these for our hypothesis testings. Okay, let's go back to the big Andes burger bound. So this is our model, unrestricted models. So we want to test whether beta 3, beta 4 is equal to 0. And now I hope you recall previously we spare off the step-by-steps of doing this hypothesis testing. And this is what we are going to do here. Follow these procedures. Okay. First, specify the null and alternative hypothesis. That's our null and alternative. Second, specify the test statistics and its distribution under the null. Okay. So this is our F test statistics. And J here is equal to, remember our null hypothesis is beta 3 is equal to 0. Beta 4 is equal to 0. That has two restrictions. And for the full unrestricted models, we have four parameters: beta 1, beta 2, beta 3. So the degree of freedom of the SSEU is number of observations 75 minus 4. So under the now, this test statistics is F distribution with numerator degree of freedom 2, denominator degree of freedom 71. Okay, that's step 2. Step 3. Set the significance levels and determine the rejection regions. So now we want to have an bear in mind that distribution of F distribution, the random variables, F distribution, distributed random variables will only take positive values. Okay, the PDF look like this. Okay, bear in mind of this. So we want to choose the level of significance of 5%. And that means that, okay, we want to find a critical value we call FC, so suppose FC, such that the area under this PDF, this area is equal to 5%. And certainly we can do so. So given this, that's our critical value, which is 3.125. Okay, so our rejection region is this. So any sample value of our test statistics, which is bigger than or equal to 3.125, we are going to conclude that our decision was we are going to reject the null hypothesis. We can also look at the p-value. Okay, so that's step 3. Step 4, calculate the sample value of the test statistics, and if desired, associate p-values. Okay, so we first estimate the restricted model, predict residuals, square them, sum them up, we get this value. Then unrestricted models, the full models. Okay, predict residuals, square them, sum them up, we get this. Take the difference, divide by 2. Similarly, for denominator, we get 8.44. So now this 8.44 is bigger than the critical value, which is 3.125. Then we can state the conclusion. We reject the null hypothesis and conclude at least at the 5% level, and conclude at least one of them is not 0. Okay, that's the procedures we want to follow in doing the F-tests. Alternatively, we can also check the p-values. Okay, so the p-values, where does this p-value comes from? Remember our F statistics. This is our F distribution. We calculate a critical value of, we calculate the sample value of test statistic to be 8.44, somewhere here. And remember, here is our 3.125, 8.44. So the p-value, associate p-value, is computing the area under this 8.44, which is very, very small. It's 0.0005. So since this p-value is less than 5%, we can conclude that we reject the null hypothesis, getting the same results. Okay, so let's. I hope it's clear to you now how to do a F-test. There's a particular F-test which tests for the overall significance of the regression models. For example, our full model is sales revenue beta 1 plus beta 2 plus beta 3 advertising plus beta 4 square advertising plus L times. Okay, so now the restriction, the null hypothesis is that beta 2 is equal to 0, beta 3 is equal to 0, beta 4 is equal to 0. The coefficients of all the explanatory variables other than the constant terms, then the intercept is 0. So our restriction model would be like this: sales equal to beta 1 plus the error term. It's called E2. And this can be tested using F-test as well. And typically it's reported in here, overall synchronous. For our Andy's burger bun examples, it is 24.46 with a p-value very, very small. Then we can conclude that at 5% levels, we reject the null that beta 2, beta 3, beta 4 are 0 simultaneously. Okay, so F-test is used for testing joint hypothesis. We have multiple equalities in the null hypothesis. Of course, the null hypothesis can be just only one as well. For example, like this. We can still use F-test to test just one equality constraints. In such cases, you should expect that F-test and the t-test should give you the same results, coincide. It is indeed the case if this t-test is two-tailed. And we can show that the t-test statistic is just, if you square them, you get F, corresponding F-test statistics. One exception is that F-test does not coincide with one-tail test. So suppose you want to say test this beta null hypothesis, beta k is equal to say beta 2 is equal to 0, with against the alternative of beta 2 is positive. In these cases, T and F, they are not the same. Okay, you cannot using F-test to test this one tail. Okay, against one tail, do the one tail test, because if you square them, you lose. F do not distinguish whether it's upper tail or lower tails differences. Okay, the F-test relies on assumptions MR1, MR6, particularly MR6, which is normality of error terms. What if MR6 fails? What if our exogenous assumptions is weakened to weak versions? In these cases, we need to use what is called a large sample test. Okay. So random variable B1, suppose it is chi-square distributed with the degree of freedom M1. Random variable V2 is chi-square distributed with degree of freedom M2. The ratio then divided by the corresponding degree of freedom is F distribution with degree of freedom M1, M2. Okay, this is probability knowledge. So in our F-test, B1 is actually equal to this. And we need to divide it by sigma squares, because we need to standardize the error terms. We just saw it previously. And this is chi-square distribution with degree of freedom J. And that's our V1. V2 is this. Is the sum of square error of the unrestricted models divided by sigma square. Okay, and that's chi-square distribution distributed with degree of freedom in minus k. If we know sigma square, then we don't need V2 at all. We can actually use V1 to do the test, which is chi-square distribution, chi-square test. However, we don't know sigma square, so we use V2 to eliminate the sigma squares, getting a F-test. Okay, and that's exact because we assume in MR6 the error terms are normally distributed. So if without the normality assumption or the strict exogeneity, remember strict exogeneity is conditional on all data, this conditional mean is 0, it's weakened to say it's weakened, suppose. Then V1 no longer has an exact chi-square distribution. Instead, we can show that it is asymptotically. Asymptotically means when number of observations goes to a sufficiently big, goes to infinity and eventually, then V1 will be chi-square distributed with J. So now the idea is that, okay, but note that V1 is still not feasible because we don't observe sigma square. But now we can estimate sigma square, right? Remember, sigma square we can estimate it. We can run regress that estimate the unrestricted models, predict residuals, sum them up, divided by n minus k. So we can estimate this, and we know that this estimate called sigma hat square converge in probability to sigma square, the true values. So we can replace sigma square by its estimated versions, and now we still get a chi-square distribution with degree of freedom J asymptotically. Okay, now we need to assume that the sample size is sufficiently large enough. Okay, this is chi-square large sample tests. And we are going to reject now if the sample value of V1 hat, remember now we call V1 hat, is no longer V1 because V1 depends on the unknown parameters. We estimate sigma squares and denote V1, denote the resulting statistic as V1 hat. Okay, so if V1 hat is equal to chi-square, this critical value, so chi-square is something very similar to the, is also similar to the, looks similar to the F distribution as well. So this is a critical value. If V1 hat is bigger than the rejection region is this, okay, bigger than this critical value, we reject the null hypothesis.